Yeah, so I stopped last week at this slide, which I called the first perceptual model, which is used for calculating or estimating the strength, the loudness or loudness level of a complex sound, which contains of multiple frequencies. And the different influences of the different frequencies are shown. Oops. Yeah. It's tricky to always let people in. That the different weights for the different frequencies are obtained by filtering the input signal before averaging the amplitude, so that this gets perceptually relevant measure for the loudness. But this is not the only way to do it. This is the most frequently used method, this so-called dBA or dBc or dBV, whatever you use, these weightings. And there's another weighting, which is more meant for weighting, broadcasting or consumer equipment, the noise, for example, at relatively low levels, in order to find out how much annoying it would be if it's overlaid with the wanted signals itself. So there are here we see the A curve from the previous slide, which is the blue line. This would be the A curve, and in addition to that, there is another standard, which is the so-called ITUR. ITU is another standardization committee, and they make recommendations. That's why it's called R468, and this number specifies this curve to weight noise in consumer equipment. So this would be another model for this specific purpose. Yeah, and coming to broadcasting, there's one interesting term which is often used. It's called loudness war, and this would be mainly for radio programs, but it could also apply for sound for TV programs. That means the broadcasters, or the people who operate the different programs, they want their program to be as loud as possible in order to catch the attention. When people zip through the channels, then they assume there's something going on if it's especially loud, and might skip faster over other programs when they are not that loud anymore. And this escalated to some extent. There were some rules given by the broadcasting authorities, like EBU in Europe, European Broadcasting Union. They said, well, the maximum amplitude must not exceed this peak value. The peak value must not exceed this specific limit. Well, people incorporated into their programs before sending them, going on air, some compression techniques of the dynamic range. So they made the low volume parts louder and limited the loud parts so that they were just below the threshold, which was allowed. But this, of course, destroyed some of the content. The dynamics also have some kind of meaning in many cases. So there was some struggle on this loudness, and this was called loudness war. Everybody wanted to get his program as loud as possible under the permitted maximum level. And they were measured with different methods, which were also specified by the authorities. And so there was a strong compression. And I want to show some examples for strong compression and weak compression. In the room, we again have only the limited capacity of the small loudspeakers. And if you are online and wear headphones possibly, then please be careful with the volume. Let's see what we have here. And I want to play first a signal with relatively strong compression. I guess you noticed that is, and you see it from the graph, it just shows the envelopes, that it's really at relatively equal amplitude or loudness at all the time. And now it's some other signal which would have some expressive meaning of the dynamic range. This would be this example. Okay, maybe that's enough to illustrate a little bit of what this means, this strong dynamic range compression. And I had a colleague in former times who called this more or less one-bit compression, because it just is either at the full threshold, full amplitude, or it's off completely. This would be the consequence of doing such a strong compression. And for making it more meaningful with respect to what we hear, how we perceive loudness, there were some loudness measured required for music or for radio programs to be standardized, so that this would give values and then the limits could be defined for this measurement, would not be allowed to be exceeded. And so there was a new measure introduced, which is by the European Broadcasting Union, the recommendation R128. And this is based on, again, a standard of the ITU RBS 1770. And this was extended by some gating. That means it just focuses on the signal segments which are actually loud enough. That means segments which are below 8 dB, below the average, they would not be counted to measuring the loudness. So that loud passages in the signal could not be traded by pauses in between, which would have been the case by directly applying this standard. And I want to explain a little bit what this looks like on the next, I guess, on the next slide. Yeah, and first of all, I want to explain what they did. They defined a loudness range. That is a generic descriptor that helps to decide if dynamic range compression is necessary. That means the range of the louder parts and the parts of lower volume. And then they measured a true peak level, which is the maximum absolute value, which ideally would be measured in time continuous signals. Because if you have time discrete signals, you could have signals which more or less resemble a signal which has peaks between two samples which are quite close to the threshold. This could be by sampling, could just the maximum in between would be omitted, but would be reconstructed by a DA conversion later. So this can be taken into account by oversampling the signal with proper filtering. So this would have to be done to find the so-called true peak level. Then you can find the maxima of the absolute values, of course. And here are the names of some standardization bodies, so that you know a little bit what this means. European Broadcasting Union, International Telecommunication Union. They have two sections, one radio communication section and telecommunication sections, ITUT. Maybe that comes later somewhere, I don't know. And ISO is International Organization for Standardization. And IEC is the International Electrotechnical Commission. So I think we saw an IEC standard already, ISO standard also with the equal loudness contours and so on. So they all are different organizations for different purposes. But sometimes they're overlapping in their let's say, fields of what they define, what standards. Like audio coding, the MPEG is a part of the ISO, International Standardization Organization. So this would be standards, the MPEG standards like MP3 and so on. These are from the ISO, and other standards for video telephony and also telephony are often made by ITU-T for telecommunications and so on. And for broadcasting, at least in Europe, it's the EBU, which is relevant for the standards to be recommended or mandatory for European broadcasters. So, and they fixed this, and also they decided to use this ITU standard. And this looks like the following. Here it's defined for 5-channel signals for surround sound. And the following steps are taken to model, to get a value resembling the loudness of the signal. So each channel would have a pre-filter. The second order filter, which models the acoustic effects of the head. Then a so-called RLB filter, which is a revised low frequency B curve, like the B curve we saw for the level measurement. And so this would be a second order filter for additional spectral weighting. Of course, these two filters can be combined to one, but they are described as by their motivations. This is then called K weighting. And then the mean square values are calculated over measuring intervals of 400 milliseconds with 100 millisecond pop size. That means one 400 millisecond segment is taken, and then it's shifted by 100 milliseconds, and another 400 milliseconds interval is taken there, and so on. So you get one measurement per 100 milliseconds of the audio. Then the items or the different channels are weighted differently. So 0 to B means there's no, that's a weighting factor of 1, but the surround channels, they are weighted with positive dB values. That means they are emphasized, and then these mean square values would be summed up after this weighting. And then a dB value, so if the mean square, we are in the square domain, then 10 log 10 calculates it, makes a dB-like value, let's say, out of that. And then there is a...
Hallo, Entschuldigung.
Hallo.
Hier war gerade noch ein Kurs. Ist hier noch irgendwas übrig geblieben von dem Kurs? Ist
Nur,
euch was aufgefallen?
nur der Flaschenkasten da hinten.
Ah, okay. Viel Spaß.
Yeah, so then there's kind of an integrator over time duration, which can be controlled by start, pause, or reset. And then this gives the program loudness. That means the loudness of the program in total. And in order to find out if the loudness measurement matches the perceived strength, again, because it's what we want to resemble with such a model, is the perception of loudness, of the strength of a sound. And so for this, experiments have been done by using a reference signal, which has a certain loudness, and a test item for being measured with a certain with a certain measurement system, like this one we saw before, or also other ones, like also competing systems. They would generate a measurement of the loudness, and you could set the signal strength so that this measurement system would give out a certain loudness level, like also 60 dB, which should be, in the ideal case, the same, perceived as loud as the reference. And if now the listener can switch between the two signals, he can decide whether they are equally loud or if one is louder than the other. So that would be the only judgment done by the subjects here in this listening experiment, by the signals which they get from the loudspeakers, which should have equal loudness. And by adjusting those, you can find out how far they are off the real loudness. So the level of the test item should be adjusted that it matches that of the reference, so that the listeners could even change the loudness of this item, and then this would be said to be 60 dB. And then the results for the different systems which were tested during the standardization, they have been evaluated, and there have been much more complicated loudness measurement systems with models of the inner ear, which we will see later. But this is a relatively simple system with just some filtering, just some averaging and weighting, and this actually performed best in the end. So here we see for different loudness in dB, if it was correctly adjusted, that should be on a straight line with the objective and the subjective loudness. And we see here that they are quite close to this line, all the measurement points with some listeners with different data sets, and the correlation coefficient was quite relatively close to 1. And this was how the standardization bodies evaluated these measurements. Okay, so now there's someone joining me again. And the next and last slide of this part is going one step further. Up to now we had loudness levels, which were somewhat connected still to the physical strength because they used a dB-like scale. And in order to get closer to actual, let's say, subjective evaluation of the strength of a sound, people did experiments and asked listeners to say, to adjust, for example, the strength of one sound, that they would say now it's twice as loud as the other sound. So this would be really perceived strength. I think it would be hard for me to judge that now this sound is twice as loud as the other sound, but apparently that's what was done in this work, which led to this to the next measurement of perceived strength, and this is the loudness. Up to now we had loudness level, and the next is loudness. And the measure, normally the letter N is used, and the unit is zone. And this is derived just from the loudness level by a mapping. And that mapping we can see here in this graph. We have the loudness level, which was given in phone. As I said, this is still connected to a dB-like scale. And now the loudness in zone is on the vertical axis. And we see that there is some mapping with this curve, which we see here. And when there's a straight line on this double logarithmic scale, because phone is a logarithmic measure, and here we see the loudness also in a log scale. This would be then just an exponential function where the exponent would correspond to the slope of that function. And that's what we see at levels above one zone or 40 phone. What we see here, there's this more or less kind of the point which might be good to remember is up to 40 phone, there's some nonlinear connection. And because the log value of the loudness itself, it can't go to 0, right? No, this can go to 0, but here we have to go very far down in order to really reach a loudness level of 0. And here, here we have this nonlinear, straight line behavior at very low, at the lower levels, and at higher levels we have kind of a straight line. And this straight line corresponds to mapping back the loudness level to a linear value or to an energy value. No, this would be a linear value with the 10. And so there would be somewhat proportional to that value, the loudness in zone, to that value to the power of 0.3. Exponent is smaller than 1. That means that larger values are less strongly weighted, rated, so the curve would be a nonlinear function going like this. And the sound pressure approximation, if we saw that from before, the sound pressure is related to the loudness like here. And so if it would be the sound, the root mean square sound pressure, then the exponent would be 0.6. Or if it's the mean square sound pressure, then there would be an exponent of 0.3 again. And that means that it's proportional to these functions. It means if we take the power of the sound pressure, that means the mean square value, we would have to take it to the 0.3. That means it's close to the range of taking the third root, and this is something which occurs more frequently in audio processing, let's say, this value. Okay, are there immediate questions regarding this, which should be recorded? Is there, yeah, you have a question?
First of all, like the sound scale is for perceived loudness, is it a linear scale?
It's the question is if this is a linear scale. It should be a personally, it should be a linear scale. That means if I go from 1 zone to 2 zone, I would say the one sound has 1 zone, the other sound has 2 zone, then I should say, well, the second sound is twice as loud as the first. That's the idea of using this loudness measure.
Okay, so after like 40 phone is same for zone and phone. So it is like 40 to 80
here you see that
go,
here,
then will be also double.
Yeah, here you would say if you go to 50 phone, then it would be perceived twice as loud. So 10 phone above 40 dB or 40 phone, sorry, it should be like that, yes. So that's then this kind of this behavior here. So in here it's twice, and then if you go then since this is, we have this this exponent, then of course the next would again, since it's the same ratio, that would be again doubled and so on. Yeah.
And when calculating this, we take into account all the SPL, or is averaged over like.
So if you have a single tone, sinusoidal tone, you would have to use the loudness, equal loudness contours before. Then you can go from sound pressure level to loudness level. Then you have the phone value, and then you go from the phone value to the zone value by this graph, let's say, or by this approximation, depending on which range you are. But if you have a complex sound, you would have to estimate the loudness level by using this dBA, dBB, or dBC measures, which are ratings, let's say, which are defined depending on the strength of the sound. And then you would get, again, from a recorded sound, of course, you have to use a calibrated microphone, from this recorded sound to a loudness level in phone that should come out of this loudness level meter. And then you can get from this loudness level again to the loudness in zone by this mapping. Yeah, so this would be the let's say, models for describing the strength of sounds.